Good morning, everyone, dear colleagues, distinguished members of the Presidium, ladies and gentlemen, esteemed guests. Please allow me to introduce myself. My name is Olena Hevko, and I am an Associate Professor PhD at Ternopil, Ivan Plurinational Technical University. Today I'd like to present our research. The topic of my presentation is Telemedicine and Psychocorrection, a new paradigm through healthcare data processing innovations. We propose a novel approach to creating a telemedicine psychorehabilitation system taking into account various methods for assessing stress responses. The methodology is developed based on the Oranta information system. The proposed comprehensive telemedicine system is able to detect stress, control it by tracking stress markers, and simultaneously correct the patient's condition, which makes it effective and convenient in everyday life. Stress disrupts homeostasis and contributes to the development of various somatic and mental illnesses, negatively impacting cognitive brain functions and the state of the cardiovascular system. Accurate and optimized monitoring of stress indicators and the ability to manage them are priority tasks in medicine, yet they remain debatable. The goal of our approach to the timely detection and correction of stress is to create a comprehensive psychorehabilitation telemedicine system based on the general algorithm presented below. There are systems for diagnosing stress based on single indicators, whether laboratory or psychological. We suggest combining subjective and objective mental health assessments in our telemedicine system. Subjective stress assessment can be effectively monitored remotely using interviews and questionnaires. There are two types of stress, acute and chronic, and they can be differentiated using questionnaires. For instance, Cohen's perceived stress scale was used at the beginning of the war in Ukraine for online surveys of Ukrainians. It is advisable to conduct an objective assessment of stress by examining both biochemical markers and physiological responses. Biochemical markers of stress can be detected in blood, urine, sweat, tear fluid, and saliva. We were particularly interested in monitoring salivary cortisol levels as a simple method. In recent years, remote monitoring methods for salivary cortisol levels have been most intensively developed, even using smartphones focusing on biosensor technologies and platforms. There are a number of physiological reactions that are easy to monitor and are informative in stress diagnostics. These include electrodermal activity, change in respiratory rate, heart rate variability, and etc. Heart rate variability is the most frequently studied as it allows for timely detection of increased sympathetic activity associated with stress. This requires analyzing the time domain and frequency domain of heart rate. The signal is typically collected using electrocardiography. However, the complexity of electrode placement and the unwieldiness of the method complicated remote monitoring. Arterial oscillography has emerged as an alternative method which allows assessing these same indicators and several additional ones that are currently being researched. Furthermore, and the software for the Oranta AO information system developed by a team led by Professor Dmytro Vakulenko makes this easy and simple. The aim of this work is to develop methods and algorithms for creating a telemedicine system for comprehensive diagnosis and correction of stress. To achieve this goal, the following tasks have been set. We conducted an experimental study on stress levels using the Oranta AO information system, employing questionnaires and arterial oscillography methodology. Anxiety and depression levels were assessed using the hospital anxiety and depression scale and the state trait anxiety inventory, while neuroticism was assessed using Eisenke's methodology. We surveyed 260 patients. Anxiety in the sample closely correlated with dominant sympathetic activity according to arterial oscillography data. Specifically, over 30% of students demonstrated high levels of neuroticism and anxiety. However, for future studies, we propose using questionnaires for stress detection with a differentiated approach to stress types, chronic or acute. Spectral measures of heart rate variability, such as low frequency power and high frequency power, very closely correlated with the corresponding anxiety level scales. Thus, a negative correlation was observed between HF and anxiety, while a positive one was observed between LF and anxiety. As the stress level increases, LF increases, and vice versa. When HF is increased, a person feels calm. In the time domain analysis, the index of tension over respiratory system positively correlated with anxiety level. In the remaining students, activation of SDNN and RMSSD was observed, which indicated the dominance of the parasympathetic nervous system. Based on the above, we proposed a general algorithm for a telemedicine diagnostic system for stress detection, based on arterial oscillogram acquisition and questionnaires that were integrated into the Oranta AO system. An experiment was conducted to study the impact of multimedia calming compositions integrated into the Oranta MIS telemetric system on students experiencing stress. As a result, changes in the spectral and time domain characteristics of heart rate variability were observed. Video images of natural elements played a particularly important role: bubbling water, flickering flames, and forest bird songs. It was experimentally demonstrated that after viewing bubbling water, the stress index significantly decreased, parasympathetic tone was activated, and HF increased from 48 to 64. Therefore, it was considered appropriate to add a module with multimedia compositions to the diagnostic component of the automated system, functioning as a feedback system. However, for a comprehensive assessment of physiological state, we recommend including in the system not only heart rate variability measured by arterial oscillography, but also the measurement of other stress markers and tracking their changes under the influence of multimedia compositions. Therefore, the system for stress physiotherapy should, in addition to assessing stress reactions using a questionnaire and heart rate variability data from arterial oscillogram analysis, also include monitoring of cortisol in saliva and measurement of other physiological responses. Furthermore, such a system should also include a block of signal selection, primarily via a mobile application, a signal analysis module in a cloud-based computational service, and a therapeutic intervention model for the patient. This intervention model should be selected based on the relevant diagnostic data using a feedback system within the user's personal dashboard. Once the data in the information analysis module has been analyzed, the expert system immediately identifies the results that deviate from the norm and selects a multimedia composition via the feedback system. Such a system will allow for comprehensive, multifaceted assessment of stress levels. Continuous feedback, which is fundamental to the system's operation, will enable individual psychocorrection during diagnosis and the tailoring of specific interventions. The proposed new stress psychocorrection system will open new horizons in psychology, help psychotherapists better study the pathogenesis of stress reactions, and therefore enable their timely detection and effective management. The authors are grateful to the Ministry of Education and Science of Ukraine for financial support of the project development of a personalized telediagnostic platform with artificial intelligence for the doctor and the patient. Hit Dmytro Vakulenko in the competition scientific and technical work under state order for scientific and technical developments and scientific and technical products. That concludes my presentation. Thank you. Thank you for your attention.